Good afternoon, everyone, and thank you all for joining us today for what is the final webinar in our three-part Applied Statistics series with Stephen MacDonald, who is a Principal Clinical Scientist at Cambridge University Hospitals. Just to remind you that the previous two webinar recordings are available for you to watch on our website, randox.com, and we will put the link into the chat at the end of today's session so that you can watch those whenever you like. And before we start, just to highlight that at the end of the session, there will also be a feedback form, which we would ask that you fill out. At the bottom of the form, there is a comments box. If you could please include any questions that you have for Stephen or indeed for Randox there, as we may not have time to get to them at the end of today's webinar. So without further ado, I will now pass you over to the very knowledgeable Stephen MacDonald for this Diagnostic Accuracy webinar.
Good afternoon, everybody. I assume everybody can hear me okay. Okay, you're not telling me I'm mute, so we will continue. So welcome to the third session. As Donald says, again, thanks for the introduction. This is the third in a session, the third session that we have done in sort of introduction to statistics in medical laboratories. We're going to do something slightly different today. In the previous two sessions, we talked about basic applied statistics, and in the second we talked about using them in analytical performance specifications. This time we're going to talk about diagnostic accuracy, so the nuts and bolts of actually what we're trying to achieve in the lab and what the specifications that we're trying to reach in the lab actually mean clinically to the patient. Also, we're going to talk about how that intertwines with what we're trying to do in verifications of assays in laboratories as well, to try and maintain that diagnostic accuracy. But mainly what I want to do today is try and rethink about how people think about statistics in medical labs and try and break the association that we have in laboratories with statistics of how we've been taught over the years, and actually try and introduce you to a more intuitive way of thinking about statistics. And it's very topical. It's certainly a discussion that's been had over a long period of time, a couple of hundred of years actually, about what is the best way to look at statistics, particularly for medical laboratories. So we're gonna hopefully try and introduce that to you today. We'll start with a definition. What is diagnostic accuracy? That's the title of the talk today, so it's a good place to start. What does it actually mean? What are we trying to achieve by this? And from this reference here, I've shown that they've quoted diagnostic accuracy, or they've defined it as being how well an individual test will discriminate between two conditions of interest. And in this scenario, we're talking about health. So that might be differentiating between sick people and well people, but it also might be trying to differentiate between different stages of disease and progression of disease. So irrespective of the type of test that we're using, we're trying to think of a positive, a negative, a sick, or a well classification of a disease of a patient. And what that usually means is where we're using some form of data to categorize a patient into one of these categories. And how we do that is by using certain metrics, some of which are written on the slide here, and these are the main ones that we'll be discussing today. Although there are absolutely dozens and dozens of different statistics and metrics that can be used to try and ascertain whether an assay has a good diagnostic accuracy or not. So some of those that you may well have heard of: sensitivity, specificity, positive and negative predictive values, likelihood, which is a word that I'll be coming back to throughout the whole talk. And also, as you may have seen in the advert for the webinar, this area under the curve and ROC analysis and how that ties things all together. But as ever, it's always good to start with an example. And this example sort of gives us a way of trying to rationalize the way that we think about statistics that we're given in the lab. So this is data from a few decades ago now, but they took a they did a study and they found that of all 40-year-old women, approximately 1% will have breast cancer. So those numbers might not be right just now, but for illustrative purposes, that's what we're using for this example. So the discussion is about whether all 40-year-old women should have mammogram screening in order to detect this 1% of patients that will have breast cancer, using a method that at the time will detect 80% of breast cancers when they're present in a patient. So that's our first metric, our first diagnostic accuracy measure that we have for the mammogram test. Of course, of these tests that are done, 9.6% of healthy women, so let's say 10% of healthy women, will have a positive result when they don't have breast cancer. So I'm going to try see if I can give you the chart here. The question I've asked you all there is, if any single woman presents and has a mammogram and then gets a positive result, what's your feeling for what the probability is that she has cancer? So I'll give you 5 or 6 seconds. Just dump an answer into the chat and we'll see. Assuming that I can see them, of course. Okay, we're getting the answers coming in now. So they're ranging from very low, 1%, to very small percent chance, all the way to the other side, which is saying very likely. Some are saying 0.8%, some are saying 80%. Good. So I think that's the point that we're looking for, is that there's quite a wide range of answers that potentially could be given by this data. And it's quite surprising to me that actually only 8% of the patients who have had a positive mammogram test will actually turn out to have cancer in a test that has 80% sensitivity. And we'll work through this example as we go through. But I think we saw from the answers that were in the chart that it can be quite counterintuitive to think there would be such a low result when we're talking about a high sensitivity test. So why is it so low? And well done to those that did say it was low, by the way. The chances are that there are many, many more women who do not have cancer. So the prevalence of the disease is only 1%. So already we know that 99% of our patient population do not have cancer. And because of the relatively small false positive rate, which is 10%, this dramatically overtakes the sensitivity of the assay. So the small false positive rate, albeit small, but in a large number of people, results in a much larger number than even a high sensitivity test in a low number of people. So 9.6% of 9,900, for example, is much, much greater than 80% of 100. So if we get a randomly selected patient into a test and get a positive result, the chances that that positive result came from one of the non-affected people is much, much higher. And therefore it's much more likely that it was a false positive. So in this example, really the point is that a result alone is not sufficient to interpret what the likelihood of a disease is in a patient. It gives us a guide, but there's a lot more to it. And those metrics, the sensitivity and the specificity that we gave in the previous slide, are relying on independent judgments of whether patients have diseases or not. They give us an idea of how the test performs, but we need to know much more than that to be able to interpret the result. So let's take an example. Let's try and develop a perfect test. What would we look for in a perfect test? And if we look on the graphs on the right-hand side, the histograms, ideally what we would like to see is a population in blue here who have no disease, all our patients who don't have any disease, and they will have a given result within a given population there, which is completely separated from the disease population. So you can see here that actually in the middle, there's a nice separation between the two populations. The non-disease population are completely separate from the disease population here on the right. So what that means is that if we then perform a test, which gives us the results according to these histograms, then we can discriminate absolutely with 100% accuracy, provided, of course, that we have a cutoff. So we need some sort of cutoff in the middle. We need a cutoff of a value that we say if the value is below this cutoff, for the patient, then they don't have the disease. And if it's above that cutoff, then they do have the disease. And so where the patient lies relative to the cutoff determines the performance. So in a situation like this, we would be very happy with this test. We would think it would have 100% sensitivity and 100% specificity because there's no overlap at all. But unfortunately, no such test exists. And invariably, there is an overlap of the population. And we will see patients who are completely normal, as we saw in the cancer example, who give positive results. And we see people who are with the disease who will give negative results. So we need to have a way of managing when these disease patients and normal patients are misclassified. And that's where we get these metrics that I've already touched upon briefly. True positive, so those are patients who genuinely do have the disease, and that is verified externally by a method that isn't the test that we're measuring just now. So they are positive by that test and they do have the disease. And the flip side is, of course, patients who do not have the disease and prove to be negative by the test as well. But these false positive and false negatives are really the metrics that determine how good our tests are. Because the development of the test will always be trying to pick up the patients in the true positive sense and the normals in the true negative sense. But as to the extent where we get false positives or false negatives that really determine how good the test is. So false positives are in patients who are normal that have a positive result by our test. False negatives are disease patients who have a negative result by our test. And for hundreds of years, there's been a really effective way of visualizing that, something called a contingency table, also known as a 2x2 table, or also as a confusion matrix in some fields now. And this isn't just used in medical applications, it's used in machine learning, statistics, all sorts of different things. And what we're trying to do is looking at our tests over here on the left-hand side. If a test is positive or a test is negative, how does that correspond with what we know about the patient? So again, to stress, the patient classification of having the disease or not the disease is not based on the results of these tests. That is externally verified. And we are then testing what our test performs against that verification and adding them into this table. So if we look at this column here, we will have a patient who we know has the disease. So they may have been found to have cancer in a different way, and what we're doing is testing the mammogram. If the test is positive, then we call them true positive here. If they're without the disease and the test is negative, that should be true negative. Isn't that amazing that you check these slides loads and loads of times and actually you've got a typo in there. So that should be true negative down there. If the test is positive in a patient without the disease, then it's false positive. And if the patient has the disease and the test is negative, it's false negative. And this 2x2 table is really helpful for us because it allows us to be able to calculate the sensitivity and specificity of our tests. Glad to see I got it right on the second slide. So the sensitivity is the ability of a test to pick up the disease in a patient. So it gives a positive result in a patient with a disease. So it's the number of disease patients picked up by the test goes into this cell here. And that is our true positive. And we divide that by the total number of patients who we know have the disease. So that is both the true positive patients and the false negative patients, because the actually diseased patients we know are positive, but the test has missed them. So we take the true positive and divide that by the true positive and the false negative result to get a proportion of patients that were picked up by the test correctly. So to look at that numerically, if we imagine an imaginary laboratory test verification where we might do a couple hundred samples in this case here, where we would compare the test against the ground truth that we know, we can see that 142 patients with the disease were identified as being positive, so that's our true positives. 128 patients without the disease were identified as being negative, so that's our true negatives. And then for patients without the disease who came back positive, false positive, we saw 7. And false negatives, we saw 6. So they were patients that we know have the disease and have tested negative. So numerically, we can take 142 and divide that by 142 plus 6. We can already see that this fraction is going to be close to 1 because we're dividing by only a slightly larger number than we have on the top. And lo and behold, we get a sensitivity of 95.9%, which is an excellent sensitivity for any sort of test. Likewise, specificity. So whereas with sensitivity, we looked at this column here for the patients with the disease, we're now looking at how do we classify patients without the disease. So we look at the number of non-disease patients picked up by the test, the true negative down here, and divide that by the total number of patients in that column, remembering that the actual non-disease patients in this case have given a positive result and are therefore a false positive. So the true negative divided by the true negative plus the false positive. Going back to the original data set, again, we're looking at this column here this time. We're looking at 128 divided by 128 plus 7, so 128 plus 135. Again, that fraction is going to be quite close to 1, and that gives us a specificity of 94.8. So again, a very good discriminatory ability to pick up our negative patients or our patients with an absence of disease in a negative manner. But there's an important question that we haven't answered, and those metrics are entirely determined by where the cutoff is. And if we move that cutoff, then obviously we're going to get a change in the performance and a change in the specificity. So we need to know, we always do when we're validating and verifying assays, if we get given a recommended cutoff either by the literature that's been published or even in our instructions for use for the assay, where does that come from? And how does that apply to our patient population? And actually, does it make any difference? And can we just go with the cutoff that the manufacturer gives us, and therefore we can just carry on and consider it verified? And these are important questions to be answered. I want to go back again to the point I made originally, where if we're looking at numerical data in particular, we're classifying patients in a categorical manner based on numerical data. So where that cutoff is placed is extremely important, and it will change its diagnostic accuracy. So going back to the original picture that we had, where they had the non-disease patients and the disease patients, if we say that a high result in whatever assay we're measuring is positive, if we move that cutoff a little bit higher, we're at risk of adding in some more false negatives. And equally, if we lower the cutoff, we'll cause more false positives. We'll show that diagrammatically in a second. So we just need to be aware that where that cutoff lies in the overall scheme of things will determine ultimately how our clinicians interpret that result. What we need to be reassured about is that when we are given a cutoff by our manufacturers, generally speaking, the optimal cutoff is set by the manufacturers. Again, we need to know what the reasoning behind that optimal cutoff is being set is, and that will again be looked at as part of our validation and verification. But in this example, we can see that the optimal cutoff here has been set at 50 arbitrary units. And because we've got two overlapping populations, the blue being the non-diseased and the red being the diseased, there are a proportion of patients here where there's an overlap based on this cutoff. So looking at the true negatives or the patients without the disease, we can see all of these patients in this distribution up until it intersects with that black line will be correctly classified. However, because the cutoff's at 50, there is a certain proportion of that population which is going to creep above 50 that, despite being clinically normal, will give us a false positive result based on that cutoff. Equally, for our patients who do have the disorder, all of these true positives all the way through this population up until the cutoff will be correctly classified as having disease. But again, this small shape round here, where we're lower than the cutoff, in patients with disease will be falsely classified as false negative. So how do we optimize the cutoff then? I mean, do we try and aim for a higher sensitivity? Do we try and aim for a higher specificity? My favorite answer to every question is it depends. And it completely depends on what the clinical use of the test is, because there will be some measurements that we are absolutely reliant on getting a high sensitivity for the test. We need to pick up patients who have the disease at all costs. And if that means that we get an increased false positive rate, then so be it, we deal with that. On the flip side, there's also tests where we want to have a really high specificity. So we need to be able to screen people and tell them that they're negative with high predictive value. And actually, if we start getting false positives and things like that, false negatives, sorry, then we need to work at how we handle that. So it really is incumbent on us in the laboratory to have a really good handle of the clinical utility of each and every test that we are using so that we can make that decision about whether that cutoff is appropriate for our patient population. Because ultimately what we're trying to do is we're trying to detect a signal through a measurement in this cloudy area where we have the overlap of the patients that might be positive, might be negative, don't have extreme results one way or the other, but it's really important that we try and classify them one way or the other. And we're not alone in trying to do this, trying to detect signals from noises, and I'll show you the solution to that in a second. But first, we'll show an example of what are the implications if we try and maximize sensitivity. So there might be situations clinically where we really want a high sensitivity of a test, and one we've lived through over the last 4 or 5 years is particularly with highly infectious agents and things such as COVID, where the consequences of missing an infected individual as a result of a false negative can be really severe, because that person can then be out infecting further people, and as a consequence you get an exponential increase in infections. So we really want a really high sensitivity there to be able to detect the presence of this disease when it occurs. But that comes at a cost, because sensitivity and specificity are very much at a balance. So if we try and aim for a high sensitivity, invariably what happens is our specificity decreases. So what the flip side of what we might see here is, with a high sensitivity, we might see that there's a lot of patients that are incorrectly identified as having a disease, and therefore they might have to quarantine or might need further testing, or they might need even a clinical intervention based on what's a false negative. So diagrammatically looking at this, if you remember, our cutoff was originally at 50. If we increase our sensitivity by dropping the cutoff down to around about 40, you can see for our diseased patients here, much more of this distribution is contained above the cutoff, and therefore will trigger a positive result. And what was previously, if you think, a triangle that size, we've now reduced that to that size for the false negative. So we're picking things up with a much higher sensitivity. However, the flip side is, in our patients who do not have the disease, the area underneath this normal distribution here is reduced, and the area which is attributable to false positives is much bigger. So by reducing the risk of false negatives, we've increased the risk of false positives. And that's a decision that has to be made to find an optimal cutoff, especially depending on what the clinical utility of that test is. And specificity, you won't be surprised to hear that the reverse is true. Excuse me, in that if we shift up the cutoff value to try and make sure that more of our negatives are contained below that cutoff value, which you can see here is very successfully done with the blue curve, we only have a very small amount of patients who are a false positive result, when we're seeing them actually, the lion's share of people are actually in the true negative stage. But as we saw in the other case, the patients that do have the disease, much less of them are contained above the cutoff point, and a much larger proportion are contained below the cutoff point and identified as false negatives. So when is high specificity important? High specificity is important when the consequences of a false positive result are severe. So the patients contained within this small section here, if they're given a really unnecessary exposure to a toxic chemical or a treatment or a chemotherapy that they didn't need, that can have quite dramatic effects on a patient. So we need to be absolutely sure that a patient isn't exposed to that sort of thing. But of course, again, the lower sensitivity has the impact in that we're going to be missing true cases of this, and therefore they're going to be missing out on the treatment that could potentially be given. So you can see that this area of where do we apply the cutoff and what are the clinical implications of those cutoffs is a real problem that we've been trying to answer for a long time. And the answer, funnily enough, comes from World War II. So there's a bit of a tangent to go off on. Where it was recognised, particularly after the attacks on Pearl Harbor, that early warning systems for attacks on naval systems were not adequate. And radar systems were having to be developed to try and detect incoming aircraft. But of course, you didn't want to be scrambling planes because there was a flock of birds flying over. That would be a false positive. But also, you didn't want to be disregarding signals that were coming in and therefore leaving yourself vulnerable to attack. So in order to try and determine what the optimal signal to noise ratio is deterministic for what the response is, something called the receiver operator characteristic curve is called. And for obvious reasons, I will be referring to that as a ROC curve from now on because it's a bit of a mouthful, and it's not particularly intuitive as to what it actually tells you information-wise. I did put this little picture in the corner for anybody. Put in the chat if you know what movie that's from, but that's what happens when you jam the radar. It's a film from the 80s. So going back to the area under the curve and its optimization, that area under the curve metric comes from the ROC curve. So how do we construct a ROC curve and what does it actually need to show us? On the x-axis, we have a measure of the false positive rate. So the false positive rate is calculated as 1 minus the specificity. So the specificity, again, as a reminder, is the ability to pick up a negative result in a patient who does not have the disease. If that was 100%, that would be equivalent of 1. If we get any false positives, then that reduces that 100% by a certain amount, and that's what we call the false positive rate. So you can see on the x-axis, that ranges from 0 to 1.00. And we compare that on the y-axis to the true positive rate as a measure of the sensitivity. So we've got sensitivity against specificity through the false positive rate here. If our test took a completely random guess at classification of a patient as normal or abnormal, we would see this red dotted line. It would be like tossing a coin. If we had an ideal test, we would like to see a false positive rate of 0, so down here, and a sensitivity of 1. So ideally, we'd be looking up in this top left-hand corner for our ideal test. That would have 100% sensitivity, 100% specificity. Every result we got, we would know how to interpret. Unfortunately, that's not the case. And what you can see is that once we get to a certain area, this curved shape starts to come where the false positives and false negatives start driving our curve away from the ideal. And what we want to find is the cutoff point that will get us, shown by this diamond here, that gives us the maximum sensitivity and specificity for our test. So if we look on the left-hand side here, I've randomly assigned a cutoff of 30, and we can see here on this black line that the cutoff of 30 gives us an excellent sensitivity, but a huge amount of false positives. So what's that? High 60s, low 70s false positive rate. So that's not going to be a particularly useful test. What that tells me is that we're going to get an awful lot of positive results, and we're not going to be able to differentiate between patients who have the disease and who don't. If we change the cutoff, you can see from the animation there that line is now shifted a bit. We still have 100% sensitivity, but our false positive rate is decreased. So let's change the cutoff a little bit more to 40. Again, the false positive rate is still coming down, but still unacceptably high. And then at a cutoff of 50, as we saw in the previous histogram diagrams, we've reached our maximum point for our maximum sensitivity and our maximum specificity. So if we were giving equal weighting to sensitivity and specificity, that is the cutoff that we would use. And that is all based on the receiver operator characteristic curve and maximizing the area under that curve. So the AUC here is 0.9828. That metric will be out of 1. That is very, very high. That is good. So sensitivity and specificity, derivation of cutoffs are all information that we will have quoted in our instructions for use. But they're never actually, we are never or very rarely told how those metrics are actually derived. And against what performance specifications they're actually derived from as well. And how do we know that the targets that are set by the manufacturers are actually achieved as well? But more importantly, the question is, are they what we actually need? Is it giving us the information that we need? Do they help us and the clinicians and patients understand what the results mean? Because ultimately, sensitivity and specificity, as I keep saying, are based on assigning a patient as positive or negative based on something that we already know effectively through another test. That's not what we're trying to do. What we're trying to do is trying to predict whether a patient has an unknown disease based on a test result. So it's the test that's coming before the classification of the patient. So two metrics which help us with that are the positive predictive value and the negative predictive value. So the positive predictive value is the probability of having a disease given a positive result. That is different from what we said with the sensitivity. Likewise, we're using the true positive results as usual. So the patients with the disease who are picked up as positive, but this time we're dividing them by the total number of positive results that we've received. So those are the true positives and the false positives. And that allows us to say, if I get a positive result, what is the chances that that's due to somebody with a disease rather than being a false positive? So that's the true positive divided by the true positive plus the false positive. So let's go back to our data that we saw before when we were doing sensitivity and specificity. We were looking at the columns. Now we're looking at the rows. So for the positive predictive value, we're looking at 142 divided by 142 plus 7. So that's 142 divided by 149. We can again see that this is going to have a high positive predictive value. And we know that by looking at the raw numbers, because all the positive results that we received, 142 of them were in patients genuinely with the disease. And much the same as we said before, the negative predictive value is the flip side of that. So we're looking at the true negatives, but this time we're looking at as a proportion of all of the negative results that we have received in those tests. So again, true negative over true negative plus false negative. We can see, and in fact we can predict without doing the maths, 128 out of 134 patients here, this is going to have a good negative predictive value as well. And looking through the numbers, that's absolutely borne out in the information that we've got there. So both of these tests have good sensitivity and specificity. They also have good positive predictive value and negative predictive value. They don't necessarily go hand in hand because different things contribute to different aspects of those metrics. So is this what we need for our lab test then? I think we're getting there. But to reiterate, the question that we need to know the answer to is, now that we know that a test result is positive, does the patient have the disease? And again, we really need to be less black and white here. Maybe we need to think of it a little bit more probabilistically. So how much more likely are they to have it? So knowing what we know, and now that we've got this result, how much more likely are they to have that? So we can calculate that by the likelihood ratio. So the likelihood ratio, much like the other metrics, is split into positive and negative likelihood ratios. So for the positive likelihood ratio, we can calculate the true positive rate divided by the false positive rate, which is those two metrics which are in the ROC curve effectively, dividing the sensitivity divided by 1 minus the specificity. So in an assay with a really high sensitivity, So one, let's say 90%, because it's a nice round number. Dividing that by an assay which also has a good specificity, so that would be 1 minus 0.9, so that would be 0.1, we would have a likelihood ratio which was very, very high, showing that we know we get a good positive hit rate when the patients have the result, and we have a low false positive hit rate, which gives us a good likelihood ratio, a high likelihood ratio for a positive result. And the likelihood ratio in the negative case is just the flip side of that, using 1 minus the sensitivity divided by the specificity. So the likelihood ratio is in effect a ratio of odds. But one problem that it does have is that it's only derived from the sensitivity and the specificity, as I mentioned earlier. It's not mentioned by it's not incorporating the predictive values from either the PPV or the NPV. And in doing so, it doesn't account for prevalence. And it was the prevalence that caused that surprising result in our cancer example earlier. The advantage of a likelihood ratio is that we move away from this unknowable truth and we understand what information the test result give us. But the question still remains, how do the odds change now we have a test result? And do we need a different way of thinking about this statistically in order for it to be able to be more intuitive? And actually, talking about the battle that goes on in the statistical world is a completely separate webinar. But I just want to compare and contrast what most of you will probably consider to be statistics, because that's what you've been taught, and that's something called frequentism. And that was developed in the 1920s through a big argument about cause and effect and correlation, where basically this is where the p-value comes from. And this is the p-value that largely we live and die by. And the p-value is basically describing the likelihood that we will have seen the data that we've experimentally derived, whether we would have seen that by chance if our hypothesis is true. So that's why we're looking for a low p-value. This isn't intuitive when we're talking about how do we understand performance of laboratory tests and interpretation of laboratory tests. There is another field of statistics which I think lends itself in a much better way to that. And that's something called the Bayesian paradigm and using Bayes' theorem. And what that's based on is that we have some sort of prior knowledge about our patient and about our tests. We then get some more data, so our test result, and based on what that test result was, we update our prior belief to give us a posterior belief, and therefore give us more certainty in whether the patient is classified correctly or incorrectly. And I think this is a wonderful thing, and it's very complex mathematically to try and work out. And funnily enough, it was invented by Thomas Bayes. He was a reverend who lived in Tunbridge Wells in England. He was educated in Scotland, so I have to mention that. But he started thinking about a lot of talk about probability was talking about forward probability, trying to predict things based on data. Whereas he was actually much more interested in the field of inverse probability and actually trying to determine cause and effect. So what we talk about when we say that is the cause is a disease and the effect is the result of the disease. We're trying to predict that cause from the effect that we see. And I'm a big snooker fan, so I thought I would show this as the example that he used to try and explain inverse probability was, if you know the length of a snooker table, so let's say it's a standard 12-foot snooker table, you can calculate the probability that will land within a certain distance from the top cushion if you hit it round the table. So if you know that that is, say, 1 foot from the end of a 12-foot table, you know, all things being equal, forgetting about friction and side spin and things like that, that there'll be a 1 in 12 chance that it will land in that area of the table. What he was more interested in was, if I see where the ball is landed, can I predict the length of the table? And can I do that probabilistically? That's much more in line of what we're trying to determine through medical laboratory testing. Can we determine whether a patient has a disease based on what that result is, all things considered? And from there, sorry, there's a quick formula, but I'll explain this as we go through. He developed Bayes' theorem. It's called a theorem because it is a truth. It has been proven in numerous different ways to be mathematically true. So the question that they're asking is, what is the probability of an event A being true given we know that event B has happened? This is conditional probability. This is the probability of something being true given that we know something else has been measured and happened. And that is based on the probability of B being observed. This is the more traditional statistical method that we would have. This is familiar to us. This is the likelihood. So this is the data that we have produced multiplied by what the probability of the first event of the second event happening divided by the first event. That's quite abstract. That's quite difficult to think of. Let's put it in language that we understand as far as diagnosing disease. So the probability of a patient having a disease, given we know their result, that's what we're looking for, is dependent on the probability of the result if we have the disease, that's the sensitivity, the probability of having the disease, the prevalence, and the probability of that positive result being present. Even more explicitly, the predictive value of a positive test result is based on the sensitivity of your test, the prevalence of the disease within your population, the sensitivity times the prevalence. Again, that number at the top is taken down to the bottom as well, but also your false positive rate and your specificity of your test based on patients who do not have the disease. So we're looking at, we have a result. How likely is it that we're generally likely to get a positive result here? What could be causing that positive result? Could it be the disease or could it be something else? How much of a predictive value does that give us? So in our example, the probability of a patient having a cancer after a positive result was 8%. That was because the mammogram sensitivity was 80%, the prevalence was 1%, the false positive rate was 9.6%, and those were the high number, that should have another zero at the end of it, the high number of patients who have an absence of disease but were tested and gave a false positive result, 10% of them that was the case for. So this theorem now gives us a way of thinking, how can we interpret our results given what we already know? So what do we already know? We know how our assays perform. We know how our assays are meant to perform, and we know how our assays perform based on the quality measures that we put in place. So none of this intuition and none of this clinical utility will work unless we maintain those diagnostic accuracy measures through achieving our analytical performance specifications, which we spoke about in the last webinar. So firstly, when implementing our tests, we have to make sure that we are attaining the performance characteristics that are stated in the instructions for use, which will include sensitivity and specificity, which will include our local patient population samples that we are due to test. We need to work out what the sensitivity and specificity of those populations are, and if we have a different population, we need to validate changing that cutoff from the manufacturer's cutoff. That's an entire different topic. We need to make sure that we are achieving the accuracy and that we are making sure that we are continuing to achieve that by setting the appropriate analytical performance specifications we talked about a few weeks ago, maintaining that through our quality management. But of course, we've got to remember that our population could change. And if the population does change, then of course the performance and the clinical utility of the test changes, and therefore the interpretation of the result changes as well. And we saw this during COVID, that a positive result at the start of COVID meant something different than a positive result at the peak of COVID, meant something very, very different from a positive result when COVID was on the way down, because the likelihood of a positive result being from somebody with COVID was highly likely at the peak of COVID. But then once we were at the trough of the waves, then if you got a positive result, the chances slightly changed then to it being a false positive result, and therefore more likely that you didn't have the disease, but it was just a false positive result due to the specificity of the test. So this is something that we need to monitor on an ongoing manner, and we have to be aware of what our patient population is. And if we start testing different patients, and this is an extremely important point, if we have diagnostic accuracy measures which are quoted by our manufacturer, they will usually be tested in very, very specific patient populations that have patient samples very much selected to try and differentiate sensitivity and specificity and maximize them. But once you get tests in the real world, that completely changes, and you start testing anybody and everybody. And in some tests, that happens more than others. And of course, then you're starting to test patients that haven't been verified as part of the clinical validation, and therefore your sensitivity and specificity will again change. So your patient population can impact how you interpret your results, but also if the performance of your assay changes as well, it can also dramatically change the diagnostic accuracy of your results. So I've got to throw in a little bit about measurement uncertainty at some point. I'll point you towards a number of good papers that have been done by a group in Greece, Chatsum Jimmy Hale and Hart Jimmy Hale, who have developed a software program to simulate how a change in standard uncertainty of any given method will affect these diagnostic accuracy measures. And one example in this paper that they showed in the bottom there, that I've showed at the bottom there, talks about glucose measurements and the change of standard uncertainty or measurement uncertainty in a glucose testing procedure and what that does to the sensitivity. So if we look on the x-axis on this graph here, this is a log transformed standard uncertainty increase. So actually that 1.0 represents a 10-fold increase in measurement uncertainty, going from 1% to 10% in the case of a glucose assay. You can see that the sensitivity is quite dramatically affected. So starting with a sensitivity of around about 83.5, increasing the measurement uncertainty will cause that to drop quite significantly, and it'll go less to down around about 70%. Now, if sensitivity is important for your test, that's not good. So if your variability of your assay or if a change in calibration of your assay causes that increase in measurement uncertainty, that has an end result on clinical interpretation of your patient's results. So that's really important to have that in mind. Specificity in this case had much less of an effect. So you can see this is a high specificity test, this is 0.99 just about. And even with a 10-fold increase in the standard uncertainty, there is a drop, but it only goes down to a 0.95. Now that might be completely acceptable. And you might say we can live with a drop of specificity down to there. But equally, going back to the previous slide, you might say that this drop in sensitivity is absolutely not acceptable, and you need to maintain your sensitivity above 80%, in which case you then know through an analytical performance specification, what your limit of your measurement uncertainty can realistically be before you start clinically impacting on patient results and patient treatment ultimately. Looking at positive predictive value and standard uncertainty, dramatic effect here, a really significant change. So you can imagine this having quite a big impact if you're testing for a disease and you're looking to detect it and your positive predictive value is high. So you tell a clinician your result is positive and they say, that's great, I know exactly what to do, I can go away and take my clinical decisions based on that. If your measurement uncertainty suddenly drops, and then you're giving them the same result, you're saying it's positive, and it's a 50-50 chance whether that's actually true or not, they're making the same clinical decision on completely different information, and that's not acceptable. So we need to maintain the measurement uncertainty within a range that actually means the same result that we give to a clinician means the same thing to them. And we saw that there was very little effect on the specificity, and because of that, the negative predictive value shows very little effect as well. So if we take the ratios of them, the likelihood ratio, we've started off with a test which has got a likelihood ratio of 70. So a positive result tells the clinician that they are 70 times more likely to have a clinical intervention required than not. And then with the same increase in measurement uncertainty, we're basically saying we can't tell. We can't give you any information about whether they're more likely to have this result. I think it was a glucose tolerance test that they did it in. That's really quite stark. And that is something that should be under control in the laboratory, should be managed in the laboratory through your quality control, through your calibration, through your metrological traceability, through your EQA, through your IQC peer review. All of these things are put in place because ultimately they're maintaining the performance of our tests to mean that the same result is interpreted in the same way consistently over time. That's the end of a bit of a sermon there. So to summarize, we're getting near the end of time now. What is diagnostic accuracy? On the left-hand side are some of the things that we've discussed, and I really wanted to highlight the ones that are most commonly provided to us by our manufacturers: sensitivity and specificity, PVV and MPV, likelihood ratios, plus and minus, less so. Because these are the ones that I've focused on today, because these are the ones that are most accessible to us. And what we really need to do, and hopefully today has helped with, is to try and interpret, first of all, what those metrics mean and how we maintain those metrics and keep them stable. What I haven't discussed, and I encourage you to Google diagnostic accuracy, there are dozens and dozens and dozens of other metrics that we could look at. And what a lot of statisticians have looked for is an overall accuracy measure. And what they've done is they've tried to combine this by combining true positives and true negatives, and rather than keeping them separate, as we do with sensitivity, specificity, they've tried to combine them into a single metric. One example, I've no reason that I've shown this one other than it was the first one that caught my eye, is something called the balanced accuracy, which is true positives and true negatives. So your good results divided by your total normal and your total negative and your total positive. The problem with giving that under an individual metric is that we are losing some of the information that we need in there. It doesn't give us the information about the clinical utility of the test and the importance of either sensitivity or specificity for the clinical use of that. So although there are limitations to some of these methods discussed on the left, I think they are still intuitive for our clinical use of assays. So to finally summarize, clinical interpretation is driven by understanding of sensitivity and specificity. That's what we get asked: how sensitive is your test to pick up this, that, and the next thing? When the information is available, we don't often get confidence intervals around that, which is ridiculous because we should. And we spoke about confidence intervals in the first webinar. Because of course their sensitivity and specificity is ultimately determined by the design of their clinical diagnostic studies that they've done. That's information that we need because we need that to be able to pass that on to our test and our test performance. It requires us to think in a slightly different statistical way, I think, and the Bayesian method, where we have a prior belief updated with new data to give us a posterior belief, I think fits in really well with how clinical interpretation of results is practiced these days. And also I think the statistical methods that we have can be interpreted in that way as well. So it's really important to consider that if we haven't already. And ultimately, it's our responsibility to make sure that we are hitting those targets and doing our clinicians justice by giving them reliable results. We also need to consider it when we're doing meta comparisons. A meta comparison is not a clinical diagnostic accuracy study. It is a meta comparison because that's what it's called. So measuring sensitivity and specificity and trying to compare that to what we have given by our manufacturers is somewhat different and needs to be handled statistically different, but that's an entire hour-long conversation on its own. Because we're not comparing against an external reference method. And we don't have that available to us. So we're comparing against a best-in-class method, perhaps, or even a reference method if we're particularly lucky, but we're still not doing it externally as would be done for a clinical diagnostic study. At that point, with 3 minutes to spare, I think I'll draw it to a close. Again, as Donald said at the start, get your phones out, have a scan of the QR code, give your feedback, let everybody know what you thought of it. Put in your questions if there's any questions in there that you'd like explored further at a later date, please let me know. I do have mechanisms for trying to get some of this stuff out there. I've got a blog and a website, which I'll try and get some stuff done over Christmas. But until then, have a nice holiday period, and I appreciate your attendance. Back to Donald.
Thank you very much, Stephen. Thank you to everyone who has joined us today. As Stephen's mentioned, just due to the lack of time, we'll not be able to ask for questions. But I'd just like to remind you that the feedback form does include a comments box at the end. So if you could please ask any questions there, we will make sure that we pass them all on to Stephen and get back to you as soon as we can. Just finally, on behalf of the Randox team, and I'm sure on behalf of everyone who's attended any of the webinars, I'd like to say a huge thank you to Stephen. It's been a thoroughly enjoyable series, and we look forward to seeing and hearing more from him in the new year. So thank you, Stephen.
Thank you all.